Hello there, Mr. Sutton here, bringing you the AB Calculus 5-8 Extra Practice Number 2 solutions on FTC derivatives of integrals. For this problem, we're taking the derivative of this integral, and we're also going to have to use the chain rule since this is more than just x here in the upper limit. So for our outer function, we're just going to end up with negative 2 times the sine of something, in this case negative 2 sine of 3x, times, now we have to multiply by the derivative of 3x, which is 3, and optionally you could simplify this to negative 6 sine of 3x. On this problem, to take the derivative of this integral, since we just have x in the upper limit, we basically just get rid of the integral and substitute x for the dummy variable here. So this just ends up being 2x plus 2. On this problem, trying to take the derivative of this integral, since we just have x in the upper limit, we just undo the integral and plug x in for the t here. So this just ends up being negative 5 over x. For this one, to take the derivative of this integral, we essentially just undo the integral and replace the t with this variable in the upper limit here. So this is just going to be 2 sine of x. To take the derivative of this integral, since we have something that's not just an x in the upper limit, we have an x cubed, we're going to have to apply our fundamental theorem and use the chain rule as we do it. So my outer function here is 2 cosine of something. Well, actually the integral of 2 cosine of something. Derivative of that is just going to be 2 cosine of the something, in this case x cubed. But now we have to multiply by the derivative of x cubed, which is 3x squared. And you could simplify if you wanted to 6x squared cosine of x cubed. For this problem, to take the derivative of this integral, I'm just going to use my fundamental theorem and undo the integral, plugging in the upper limit here for the variable. But because I have a 3x instead of an x, I'm going to need a little chain rule. So initially this is negative e to the 3x plus 2 times, now I have to multiply by the derivative of 3x, which is 3. So this is just going to be negative 3 e to the 3x plus 2. For this one, taking the derivative of this integral, we're just going to use our fundamental theorem. And since we have an x in the upper limit, we're just going to replace the t with an x here in the integrand. So this is just going to be 2 cosecant squared of x. And since it's just x, there's no chain rule to worry about, so we're done. To find the derivative of this integral, we're just going to use our fundamental theorem of calculus and replace all the variables in the integrand with this upper limit of integration variable. So we're just going to write x squared plus 6x plus 4. And since this is just x without anything else going on, the chain rule doesn't really need to be written out here, so we're all set. To take the derivative of this integral, we've got an x in the upper limit of integration. So all we have to do here using our fundamental theorem is replace the t with an x. So we've got negative 5 over x minus 3 quantity cubed. And since the chain rule would just give us a tail of 1, we don't have to write it, so we're done. To find this derivative of an integral, all I have to do here is get rid of the integral and replace the t with an x. So this is just going to be 1 over x squared. On this problem, to find the derivative of this integral, I'm just going to use my fundamental theorem to get rid of the integral and replace the t with an x. So this is just going to be 3 parentheses x plus 1 quantity to the 1/3 power. For this problem, since I'm taking the derivative of an integral that has a variable in the upper limit of integration, I'm just going to use my FTC and replace the dummy variable with this upper limit expression here. So this is going to be negative 2 times parentheses x squared minus 3, all of that raised to the 1/3 power. However, because this is an inner function, we have to use the chain rule and multiply by the derivative of x squared, which is 2x out here. So if you wanted to clean this up a little, we could write negative 4x times all this stuff to the 1/3 power. To take the derivative of this integral, I'm just going to use my FTC and replace my dummy variable with this upper limit variable here. So I can write e to the 2x minus 2 times, we got to use the chain rule here, the derivative of 2x, which is 2. So this is just 2e to the 2x minus 2 then. On this problem, since I'm trying to take the derivative of an integral that has a variable in the upper limit, I basically just replace the dummy variable with this upper limit variable, so replace t with x. And if this was something that had a derivative other than 1, I would multiply that by that as well. But since it's just a derivative of 1 for this x, we can just write negative 2 e to the x minus 1, and that's the end of it. On this problem, we have this graph of f, and we're defining h as the integral from 0 to x of f, and we just want to figure out h prime of 3. Okay, well, the key on this one is recognizing that h prime of x in general is just, using our fundamental theorem here, is just f of x, because you're just replacing this t with this upper limit variable x and getting rid of the integral. So since h prime of x is really just f of x, that means h prime of 3 is really just f of 3. And f of 3 we can read right off the graph here. That's just going to be this value up here of 4. So that's going to be choice B. On this problem, we have a table with some selected values of some differentiable function h and its continuous first derivative. And we're defining f as the function that's just the integral from 0 to x of h of t dt. We want to know the least number of possible critical points for f on the interval from 0 to 5. So basically, since f is based off of h and h is differentiable, the only place you're going to get critical points for f is where f prime is 0. So we're basically asking how many places between the x values 0 and 5 can f prime take on a value of 0, because those would give you critical points. Well, in order to figure out where f prime is 0, we need to have a function for f prime in the first place. Since f is this integral of from 0 to x of h of t dt, using our fundamental theorem, taking the derivative of both sides of this, we can write that f prime equals, and then we're just plugging the x in for the t here, f prime of x equals h of x. Since these two are equivalent, asking where f prime is 0 is really the same as asking where h is 0. So let's go to the table then and see where h has to be 0. Now the key on this is that they told us h is differentiable. Therefore, that means that h is also continuous, and the intermediate value theorem can be used to figure out places where h has to have a value of 0, at least intervals on which h must be 0. For example, we have the interval here from 0 to 1. Notice that h of 1 is a negative number, and that's obviously less than 0. And notice that h of 0 is a positive number, 1.08. Well, since we're going from a negative to a positive and we have a continuous function, that means we have to pass through 0 on the way there. So therefore, h of some c value on the interval from 0 to 1 has to have a value of 0. There must be at least one place between 0 and 1 where h is 0. And therefore, f prime has to be 0 there, and therefore f has a critical value somewhere on this interval. So going along the same vein, looking for other sign changes in our table, we notice that here from 2 to 3, we're changing from negative to positive. Just to write it out officially here, h of 2 is negative 0.14, which is less than 0, which is less than 1.8, which is really just h of 3. Therefore, this tells us that h of c equals 0 somewhere on the interval from 2 to 3. So this tells us that since h of x is 0 at least twice, that means f itself must have at least 2 critical points on the interval from 0 to 5. So that's going to be choice C.